Hello everyone, how are we doing? How have we been doing with our simple shell task? Earlier today we had a PLD session, and in that session we spoke so much in details about the exec function, execve, fork, and we spoke a bit about wait. So we had a recap on the previous session. So in the previous session, we spoke about the PID and PPID. That's the process identifier and parent process identifier. So we were introduced to the functions get PID and get PPID. If you've not been able to watch those videos, I've also uploaded them on YouTube. You can just go through and then you will see the videos. Please kindly watch for better understanding. So we also spoke about the execve. We spoke about the execve being a null terminated array strings, so which we can loop through in order to access every argument without needing the argument count. Then we discussed getLine. So like I've said, today we talked about the execve. So I'm just going to quickly go over what we discussed today. So in the last session, that's yesterday's session, we spoke a bit about a zombie process and about what a zombie process is. So today I just did a little demonstration of what a zombie process is. So in definition, say the zombie process or a defunct process is a process that has completed execution, but it still has its entry in the process table. So what is the process table? So we remember this is a process table. So a process table has the PID of the process. It has the status of the process. What I want to do is the one we used before, we used the flag ELF before. The flag ELF, apart from giving us the PID, it also gave us the parent processing ID. But now it's not really about the parent processing ID. I want to talk about the zombie process. So I designed the program here. So in this program, you have the puts function, and this says just to print out the program I started. Then immediately I called fork. Now if you don't understand how fork works, I will talk a bit about it later. So if fork returns 0, that's if this PID is equal to 0, that means it's the child's process. So we are printing the PID of the child, and then we are asking the child to sleep for 5 seconds, and then we say that we print out that the child has terminated, because every process in the child process here, every command, or let me say every function in the child process here, every statement gets executed and the child process gets terminated. So else here in the parent process, before I call the wait, which we will discuss later, I've asked it to sleep for 35 seconds. I'm asking it to sleep for 35 seconds so that we could appreciate the process table and see what is going to go on. And I printed the PID of the child process here so that we can use it to find it on the process table. And then after that, the parent will terminate. So the reason why we need this is, let's see what happens if we are trying to build a shell. What if we keep on calling programs on the shell and those programs get terminated in the process we create for them? Because soon we are going to talk about process creation. What would happen? So that is why we need this information. So let me run this program. So inside here, I'm going to compile GCC zombie and then the output will be zoom. Good. So I'm going to run zoom. So we can see I'm a child process. This is the PID of the child. Now the child is terminated. Let's see what happens to the child on the process table. So I'm using this AUX. So we come down here, we can see this is the child's process here, 23281. Here 23281, that's the ID. So this is 23281. So we see this says it is a defunct. Look at the status. We have the Z plus. The Z stands for zombie. So the Z plus. So it becomes a defunct process. So it becomes a defunct process. So it's a zombie process. What does that mean? What is the implication of that? Remember that the shell is a command line interface, and this command line interface is where you are going to run all your programs. So when a program is created, a new process starts for that program, which will be a child process. The child process must terminate. So what happens if the child process keeps on terminating and then it keeps populating your process table? Your process table has a limit. There's a limit, and that limit may vary depending on the system or the computer that you are using. Now, on my own computer, I created this shell yesterday, a shell script. So let me just run that shell script. Okay, I created it with a sudo. So with so let me run it as a super user. So you can see for my own system, it has a rather large allowance. But what if you have a smaller allowance, and while your shell is running and has run different processes, and all of them keep getting populated by a zombie process? They keep getting populated by a zombie process. So it means that sooner rather than later, your maximum process number will be exceeded, and then you will not be able to run other programs. So that means you must rather do something to avoid a zombie process. So I believe this should have, yes, the parent has terminated. So because the parent has terminated, I'm sure this should have been removed from the table. I need to exit from root. So if I call this again, we don't see our program anymore. So that process has gone. But the reason why it's off is because the parent also got terminated. But remember, your goal for building a shell is that you don't want that shell to terminate. Your shell is not going to terminate, because rather it's going to be in an infinite loop, a loop of reading, executing, printing, and then it comes back to read, execute, print. So it's always going to have this bash shell now did not exit. It's still there. It did not terminate. So if I have a shell that I keep on creating zombie processes, very soon that shell will become useless, because I will not be able to create another program, and I will not be able to open another program on that shell. So that is why we need to always remove our zombie processes. We need to make sure they get terminated. So for it to be terminated, let's go back to our program. So this time around, we will add the wait call. So let me uncomment the wait. So what the wait call does, actually, we will go through it. is that the wait call waits for an exit signal from the child. Remember, this is the parent, so the parent is going to wait for an exit signal from the child. So when this child terminates, the parent would know that the child has terminated, and once the parent has seen that the child has terminated, then the parent can continue its own execution. What the parent would do is that the parent would take the child, the parent will remove the child process from the process table. That is what the parent does. The parent removes that child process from the parent table and from the process table. So let's see this wait call in action. So I'm going to run this program again. Let's compile. Now let's run it again. So okay, our child has terminated, so let's rerun this. So now we are not seeing the defunct process anymore. The child process is not 23701. 23701 is not on the process table. Why is it not on the process table? Because of the wait call. The parent waited for it to finish executing, and the parent removed it from the process table, so that if at all, if this is going to be our shell program can remove that program from the execution table, and then we'll be able to continue adding new one without overpopulating the execution and the process table. So I think that's a good explanation for the zombie process. You can read more about it, you can have more practice on your own. So with this, I think we can continue. We are going to continue to proceed. I'm going to proceed into executing a program. Okay guys, the system call execve allows a process to execute another program. So it allows a process to execute another program. Note that this system call does load the new program into the current process memory in place of the previous program. On success, the execve does not return to continue the rest of the previous program. So this execve is actually part of the family of system calls called exec. So you can read about the exec system call family. So what they basically allow you to do is to execute a particular program, to execute any program from a process. So they allow you to execute a program from a process. So this is a list of different exec functions. You have the execl, execlp, execve, execvp, execle, execve. So maybe I will add this link to the group, to this video, so that you can have a read about it. So but for our own shell, we are looking at the execve. So this is the execve. Alright, instead of using this, I'll prefer to read the man page. So let's read our man page. Not necessarily everything in the man page really, but let's read something from the man page. Okay, so the execve executes a program referred to by the path name. Let's start from here. So the function is to execute a program. This is the syntax. Yes, this is the syntax. You include unistd.h, that's the header file, and then this is the prototype of the function. So the function takes in a string. The string, that's the string would be the path name, and then it takes the argument array, and then it takes another string, another array of strings, which is the environment variable. So it takes your environment. So you must pass in an environment, you must pass in the argument array, and then you must pass in the path name. So of course, if you remember this, for example, if I type man get line, now when we talk about command line arguments, remember that we're talking about argv now. Remember that arg0 is usually the name of the command, or the path name of the command, and then arg0, arg1, arg2 are the others that follow. So arg0 is usually the name or the path name of that command. So we need to take that into note. So it means if we have our argv, we have the whole we have the array of strings for our arguments. So in index 0 will be our path name. So when we are using this function and we have that array, we could just pass here index 0, that's argv0 here, while we pass in argv here, and then we pass in our environment. Well, you could pass null into this if you don't have an environment variable yet. So you could pass null into this just for testing purpose. So like we said, it executes a program referred to by the path name, and then this causes the program to it causes it to replace the current program that is the current program. Yes, so it replaces the process of the program that is calling it. Let me expand this for better visibility. Good. So this causes the program that is currently being run by the calling process to be replaced by a new program with newly initialized stack, heap, and data segments. So it definitely means that when this call, let me go to the return. I want you to take your time to read this for better understanding. So it says on success, execve does not return, and the reason why it doesn't return is because it replaces the program, it replaces the process that is calling it in the memory. So that process gets replaced by a new process, which is a process of the program that was called. So it doesn't return. But if there is an error, then it will return -1. So if there is an error, it will return -1. So let's just see this in an example. So in here we have a program. The program should be execve.c. So let's see. Okay, so just for you to note, I actually use the prototype of main. I use int ac for the argument count, and then the argv for the argument vector. So because I'm compiling, I'm not compiling with any flag for my compiler, this would run. But just in case you are compiling with flags, then you should ensure that you deal with the unused variable ac. So that would deal with that. So our program started, of course. So we put here that we have called execve. Now we initialize this argv. So at the first index 0, we are calling the ls command. I want you to note that we call the full path of the command. We will learn how we can deal with the path variable later on, but we have to call in the full path of the command. Then we have to call in the argument. So the next arg1 is the flag we are using. I could decide to also put another one. Let's say, let me call this argv2, and then let it be my root folder. Then of course this will be arg3 now. So it then means that, and then you must remember that you have to null terminate the argument vector. It must be null terminated for this to work. And I'm going to show you the error. Let me show you the error that would occur. Let me clear that. So I call the execve function. Now here I could decide to, I call the execve function, I passed in argument 0, and then I passed in argument as the vector, the argument vector, and then the environment right now I set it to null because I don't want to use any environment right now. So I could decide to do something like int I equals to execve and call this, and say, and now come here and say if I equal -1, then print failed, and then write program ran successfully. But I feel this is not necessary, and the reason why it's not necessary is that if this was successful, then the program will not run this. All of this will not be executed, but rather if this is not successful, then of course it's going to return, and then of course this would always be true. If this is not successful, this will always be true. So this if equals -1 will always be true. So that is why I'd rather just remove this. But of course, if you have a program, maybe you've written your own program, and maybe you feel like you want to include that, you can include that. So it just based on my own thinking, so you could include that on your own. So if I run this, remember I've commented this out, so that means I did not null terminate this. So the program has compiled, so let's run it. You see that the program ran, but you can see a whole lot of, it's reading into my path, into my environment, into my, yes, it's reading into my environment. So all the environment variables that have been set is reading through it, and it has no business running there. The reason is because it has traversed beyond what it should go through. So it has reached beyond what it should reach into. That is the reason for that. So I'll go back here, and then I'm going to terminate this. I'm going to remove my comment. So guys, don't make that mistake when you are writing your code, or when you're writing any program. Do not make that mistake. Sorry. Okay, now so you see this one ran successfully. It ran successfully. So let me look for a failure, something that will fail. Let me give a wrong path. Let me give it a wrong path. So let's say here I put let me put a dot there. So you see, we're able to print the failed, and then we now wrote program ran successfully. Of course, we know it did not run successfully. So don't think that your if statement would work and then this will get printed if your program got executed. So the way you can do this is that the logic here that you could use this for, or where this could be useful, is that you can have a block of code underneath this execve function that you want to run if the execve function fails. You may say, okay, if this one fails, maybe I want to run another code, I want to run another program, I want to try another program out. So you may just put those things underneath the execve function so that if this fails, then of course the next line will be executed. So that is a way you could handle this. So I think that's that concerning the execve functions. I would implore that you test what you learn, you try to exercise more. So back to our concept page. So back to this page, we are going to go to the next concept. The next concept is creating processes, and this is where we look at the function called fork. We look at the function called fork. Now, just for you to think, why do you need fork? Remember here we spoke about the execve function, and we saw that the execve function actually literally it overrides, when we call it, the program we execute overrides our own program. So let's say we are building our shell and then we call that function, we try to execute a program, it overrides our shell and then our shell is gone. But if you look at the bash program here, everything I run does not override this bash shell. So therefore, what do we need to do? We need to be able to say, okay, I want to run a program. Maybe a user is going to input a program. We want our program, our shell, to run that program without it quitting our own shell, without it taking the place of our own shell. So that means we must begin to think that, okay, every program I would want to run, I would want it to run in a new process. So that program would have its own process. So I'm going to give it its own process so that it doesn't disturb my program. So that is the goal for this new concept, creating a process. And there is a very simple way to do that. So the system call fork, man2 fork, creates a child process. That's a new child process, almost identical to the parent. The parent will be the process that called the fork. Once the fork successfully returns, two processes continue to run on the same program. So it's like you duplicate the parent process. If you're in biology, if you understand biology, I'm sure you would have come across amoeba. Amoeba would they call it binary fission. So there is going to be a separation, and then you have two sister cells. That's biology anyways. So in this case, fork is like that. It's going to separate, it's going to duplicate. It's like a duplication because they are almost identical. So it will duplicate that process, and then you have a new process that is running, and that new process is going to have access to its own memory space. It's going to have access to its own environment, and then it's going to have access to its own properties, and then in that property you can decide to run your program. So let's have a quick look at the manual. I like running my manual separately here, so let me use this. Okay, so we can see the fork call creates a child process, and this is the syntax. So these are the two header files. You have to include these two header files, and then this is the prototype of the function. The PID t is actually a type def for an integer. So you call the fork, you don't have to pass anything into the function. So it creates a new process by duplicating the calling process. The new process is referred to as the child process. The calling process is referred to as the parent process. So the child process and the parent process run in separate memory spaces, and at the time of fork, both memory spaces have the same content. They have the same content. Memory writes, file mappings performed by one process do not affect the other process. So at the time you call the fork, they are identical, but different things can now begin to occur within them. So that is what this is saying. So I want you can read about all of this, but I want us to check the return statement. So on success, when you call the fork and it's successful, the PID of the child's process is returned in the parent. So this information is very, 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 very necessary. The PID of the child's process is returned in the parent, and 0 is returned in the child. Remember, when you call fork, it duplicates the process. So now you have two processes. So when you are writing your program, the moment you call fork, the next line in your program, you have to be aware that now I am dealing with two processes. So it means my program becomes 2 in the memory. So for you to now know, okay, this is what I want to do with the parent process, this is what I want to do with the daughter process or the child process, then I have the return value. I have this return value to help me to identify which of these processes I am working in right there when you are building your code. Because when you are building your code, you don't know the ID that your program would eventually give you. You don't know. So the only thing that you would be aware of is that 0 will be the return value in the child process. Because when you're writing that program, you don't know what's the ID, the PID of the parent would be, and you don't know what the PID of the child would be. But what you know is that 0 will be returned in the child. And then because the PID, your PID, if you look at this PID table, if we come back to the process table here, you would note that the PID here, PID starts from 1, and 1 will always be assigned to the init process. 1 will always be assigned to the init process. So that means in this place now, right now if I'm creating a new process, all these PIDs cannot be assigned to that program because it has to be unique. So it is the least available number that will be assigned to the process that is going to that will be created if I run a new program in this bash. So that means your PID cannot be 0 if it is successful. It cannot return 0 for that child process. So you don't know what it would be, but you know that it will always be greater than 0. And then if it fails, you know that it will be -1. So you can use -1 to test for failure. You can use 0 to identify that you are working with the child process, and then you can use anything greater than 0. You can use if greater than 0 to identify that you are working with the parent process. So then, why is it that the child process, the PID of the child's process is what is returned to the parent? Why is it so? Why is the PID of the child's process returned in the parent? Let me borrow this. Let's read about let's check the wait call. Oh, sorry. Okay, so here we have the wait call. The wait call is in a family of 3: wait, wait PID, wait ID. So this is the prototype. You have to include this, and then for wait, and then you pass in a pointer to the status. Of course, if you don't know the status, you could just pass in null. Then for the wait PID, you pass in 3 things. You pass in the PID of the process you are waiting for. So if the parent is aware of the child's process PID, then of course you could just put that return value here, because it's going to return this fork. This fork is going to return the PID of the child's process in the parent. So in that parent, you could just use that. This is where we are. Yes, you could use that PID and pass it into the wait PID function. And then of course you could pass status, you could pass these options. So we'll come back to this later. So let me, just for you to understand why it is the parent that needs to have the PID of the child, so that the parent can manipulate that child in any way. Or the parent can also use the PID to wait for the child. Alright, so let's see this programmatically. We wrote a program. This is where I run my programs. ls. There's a program here called fork. Okay, so we had actually played around here. We did so many things here, but let me comment out a whole lot. So I've commented out this block of code, and then I've called fork here. So I'm going to print this. So I just want you to think, what do you think would happen if I print this, if I run this? If you are thinking that 2 lines will appear for this code, then you are right, because of this fork. Fork will duplicate the process, and this will run in both processes. So let's see that. So beautiful. So you can see this says my PID is 25919, and it says my daddy is 1247. Let's go to our process table here. What is 1247? 124. Oh, sorry, it's 12147. Yes, 12147. So here we can identify that 12147 is a bash process that is running, and that is this bash because we ran the program inside here. So it is this bash that gave birth to our program, which is this executable F. So its parent, that is daddy, is 12147. So this process 2591 now gave birth to this guy through the fork call, which now has a PID of 25920, and then so this one says my daddy is 25919. So how about let's see the return value of fork in both processes. Let's see the return value of fork in both processes. So right here I would add another line of printf, and then I would say printf and the return value of fork is %d . So here I'll just since we said A rather, so we said A equals to fork, so A equals to, so we use A, yes. So let's see the return value of fork in both the parent and the child process. So run our code again. So beautiful now. So of course we know this is the parent process because it's the one that was executed by bash. So bash called this, my daddy is, but this is the process, the PID of the parent process 26103. So the return value of fork in 26103 in the parent is 26104. Wow, what is 26104? We can see in the child process the PID of the child is 26104. Beautiful. So the fork call in the parent returned the parent and returned the PID, the processing identifier of the child in the parent, but in the child it returns 0. So what can you do with this information? What can you do with this information? If I call yes, I can write my code now. I can now decide to say, okay, since I have access, I have a way to know when I'm in the parent and when I'm in the child. I could have let me clear all this. I could do something. Let's apply logic with this. So if A equal 0, then I want you to print, let me just take this out. I want you to print the puts I am the child, else put I am the parent. Let's compile again. So let's run it. So now we are seeing, let's cut our code here. So this is the, oh no, I'm cutting the wrong code. Sorry, let me cut again. Cut fork. Okay, so please ignore this block. It was just a play. We're just using that to understand more. So PIDTA. Okay, so this is our code. Program started. We called fork, right? We said if A is equal 0, else. So here is going to print I'm a child, and here is going to print I'm a parent. So we are not saying this code repeated. We're not seeing this code repeated in both processes, and we're not seeing this repeated in both processes. Why? Because we separated them based with this condition. We were able to identify that, okay, if you are in the child process, print this. If you are in the parent, print this. So this was what we did. That is why the outcome of our code, the output, printed I am the parent, and here said I am the child. So with this knowledge, you could decide to run different programs. We spoke about execve. You could decide to call your execve in the child. If you call your execve in the child, and then it is your child process that the new process and that the new program execve is calling is going to run. How do I put it? It is the child's process that will be taken up by the program execve will call. So that is the application of this. But of course, remember about zombie processes. Remember that we spoke about the wait call. So I will leave it there. I want you to try as much as possible to get more practice. You could pause your video on this. Let me uncomment this, and then you could play around with this. So you could have printf my PID is %d my daddy is %d, and then a new line. So then of course you call get PID, and then you call get PPID. So the goal of this program, number one, before you execute this program, I want you to think. I've called fork 1, 2, 3 three times. I want you to think how many lines will be printed, and after you've printed those lines, I want you to appreciate how the wait function works and how those things are printed. Appreciate how those lines are printed. You could do something. You could start by removing this if statement. See the outcome of your program. Then include this int statement, this if statement, and then see the outcome of your program again. And then you try to understand what happened. If you have any questions, you can reach out on WhatsApp. So thank you very much. That will be the end for the fork process today. I think we just have the wait call. We've already mentioned the wait call. It's just for us to go over the wait call. Okay, so on the wait call is actually what we've spoken about before. Remember when we checked for the zombie process? Remember, okay, I didn't use it in the fork. I didn't use it in the fork program that we wrote. So let's check the man page. So if I do man wait, so let's just have a quick reading. So you can see there are 4 groups, but what they do is wait for process to change state. So we need to, whenever you need your program to wait for a child process to change state, then this will be necessary. So you need to include all this, and then if you are calling just wait, this is going to be the prototype. If you use the wait PLD function, this will be the prototype, and then if you use the wait ID, this will be the prototype. So I'll just go through the wait. They actually all do different things. They do the same thing, but the other options, they give you extra manipulations, or they give you extra abilities. So let's just quickly look at the description. All of these system calls are used to wait for state changes in a child of the calling process and obtain information about the child whose state has changed. So what is a state change? A state change is considered to be, number 1, the child terminated, number 2, or the child was stopped by a signal, or the child was resumed by a signal. So in the case of a terminated child, performing a wait allows the system to release the resources associated with the child. If a wait is not performed, then the terminated child remains in a zombie state. So this was what we demonstrated earlier when we spoke about the zombie state. The reason why we had the zombie state was because that child process was not ripped off the process table. So the memory allocated to the child was not released. So but when you have included, if you have included a wait call, the parent process is able to wait and know that this child has finished execution, and then it will remove the child from the process table. So everything that was allocated, the space of the memory block allocated to that child, will also be freed, and every parameter that was given to the child would be freed. So if a child has already changed state, then these calls return immediately. Otherwise, they block until the child changes state. So, or a signal handler interrupts the call. So the wait and the wait PID. The wait system call suspends execution of the calling thread until one of its children terminates. The call wait is equivalent to wait, of course, wait PID this. So but for wait PID, I just want you to actually read through this. You can set a value for the PID. Here you don't, in wait, you don't need to set a value for the PID, but you can pass in the address of an integer, and then that integer will be used to record the status. So it's going to record the status of the process that terminated. So that's where this is. So if W status is not null, you can pass null if you don't want to read the status, but if you want to check the status. For example, remember, if you run a program, when you run a program that is main, for example, you have return, you can say return 0 at the end of the program, or you could use exit status. We could say exit 98, we could say exit 99. So if you run a program that exited and gave a particular integer as its exit status, you can record the exit status by passing the address of an integer in. So it records that exit status for you in that integer, and then you can read. So you can access the value. Let's read this. So if W status is not null, wait and wait PID store the status information in the int to which it points, and the integer can be inspected with the following macros. So these macros are function macros which take the integer itself as an argument and not a pointer to it, as it is done in wait and wait PID. So so these are the different things you can read through this and see what the information you can get from it. So you see this, for example, returns true if the child terminated normally. So but if not, it will not return correct, it will return false. So you can just read through this. Then also for the wait ID, you can read through the wait ID. It does virtually the same thing, but this gives you, see, it provides more precise control over which child state changes to wait for. So you can perform more logic with the wait ID. So whichever one you choose to use for your function will be determined by you. So just make sure you read this manual, and I'm sure you can do a whole lot of things. I don't think I need to write another program to demonstrate this. Just refer to, you can go back in this video to where we demonstrated the zombie process, and then you see the function of wait in that program. So of course you would use this in your shell, so you could try to sit down and understand where this will be needed when you are coding your shell. So thank you very much for spending this much time with me in this video. I hope you have learned a lot, and then I will see you in our next PLD session. Thank you very much.